So for number 48, we want to find out if the sequence over here, if it converges. And now a sequence an converges if an tends to a specific, a defined limit as n approaches infinity. So we're going to take the limit as n approaches infinity of our an, so our sine of 2n over 1 plus root n, and we're going to see if this spits out a number for us. And so let's actually break this down into two parts. So we're going to, this is the same thing as sine of 2n times 1 over 1 plus root n, just so that we see how these over here behave, right? So if we take the limit as n approaches infinity of 1 over 1 plus root n, what's going to happen is the top is just going to be 1, right? And then on the bottom, we're going to have 1 plus root of infinity is still infinity. So this is going to be 1 over infinity, which is 0, right? It's going to 1 divided by a very large number. That is going to give us essentially 0. And so the first part of it goes to 0. But what about sine of 2n? The limit as n approaches infinity. How does this behave? Well, sine of 2n, it's just going to, if we plug in n is equal to 1, it's going to be sine of 2, sine of 4, sine of 6, and so on. And so if we plug in, if we evaluate it at infinity, it doesn't actually get somewhere, right? Because the thing is that sine, it oscillates between -1 and +1. So it takes up all the values between -1 and +1. And so if we evaluate it if we just keep adding numbers to it, right, it's not actually getting closer and closer to anything. It's just oscillating between these two faster. So if you plug in, I don't know, sine of 2 million, it's still going to give us a number between -1 and 1, and it's going to keep changing. So this limit, it does not have a limit, right? So how can we evaluate this if it does not have a limit? Well, we're going to use something called the squeeze or the sandwich theorem. And the sandwich theorem basically says, okay, if, and I'm going to represent it with functions, but it's just as valid with sequences. If, let's say this is the point x is equal to a here, and that is L, right? So this point here. So if I have a function here, this function is g of x, and we can see that the limit of g of x as x approaches a, that's going to be L, right? And then I have this other function, we're going to call that h of x. And the same thing, h of x is less than or equal to g of x the whole time, and the limit as x approaches a is also L. And so if there exists a different function between them, maybe we're going to call this f of x. So we're going to say if g of x is greater than or equal to f of x, which is greater than or equal to h of x, and the limit of g of x and h of x as they approach a is equal to L, then it means that f of x, the limit as x approaches a, must also be L, right? Because f of x is sandwiched between these two. And we're going to say, and the limit as g of x as x approaches a is equal to L, and the limit of h of x as x approaches a is equal to L, then the limit of the one on the middle must also be equal to L, right? So what we're going to do here is we're going to take this sequence over here. I'm going to take this guy, sine of 2n over 1 plus root n, and then we're going to sandwich it between two sequences, right? And the first sequence that we're going to sandwich is 1 plus root n. And the reason that we can sandwich is because sine of 2n at most is 1. It's never going to be greater than 1, right? Sine of n is bounded between 1 and -1. And so we can say that it's definitely less than 1 over the same denominator, and definitely greater than or equal to 1 negative 1 over the same denominator, right? So now that we've sandwiched this, what we're going to do is we're going to take the limit of 1 over 1 plus root n as n tends to infinity, and the limit as n tends to infinity of negative 1 over 1 plus root n. Well, this guy just goes to 0, as we've shown previously, right? 1 plus 1 divided by this root n, as n goes to infinity, that's infinity. 1 divided by infinity is 0. Same thing here. We have negative 1 divided by 1 plus infinity is just infinity, so negative 1 divided by infinity is 0. Okay, so since our sequence is sandwiched between two sequences, and the limit as n approaches infinity of these sequences 0, we can say that this limit here is 0 by the squeeze theorem. And so we say that an tends to 0 as n tends to infinity, so an converges. And that is, and we've been able to determine that an converges by the squeeze theorem and finding the limit.